Hi everybody, hi for all the participants at the Actuator conference from all around the world. This is me, Hassan Hariri. I hope you are safe and in good health. I'm currently assistant professor at Rafiq Hariri University. So at the College of Engineering, and we are a bit accredited university college. Today talk was done during my postdoc at University Sherbrooke under the supervision of Professor Patrice Masson and Professor Luc Frechette, and it's about roid noise reduction inside car cabin using active structural acoustic control. So to start, successful vehicle monitoring, safety and comfort requires what? Requires access to measured data like vehicle roll, pitch and yaw, road tire friction coefficient, transmitted forces and torques, tire pressure, speed, temperature, all those measured data, required access to them, required to measure them in order to successfully monitor the vehicle for safety and comfort. And therefore, this information, all the information was talking about, they need to be measured and processed by a sensor feedback control unit. The sensor feedback control unit, as shown here, to maintain control of various safety features, like if you wish, like electronic stability control, like traction control system, like anti-lock brake system, like active rollover protection, and to improve active noise control, active noise control, which is the topic of our talk today. So that's the journey of this research project, starting by checking if it's feasible or not to use a sensor on tire. Maybe it's not feasible, so why to use? Then if it is, where is the best location of putting that sensor? Is it outside? Is it in the sidewall, in the tread, inside, outside? And what are the specifications? Now we need to choose a sensor that satisfies our specification. Then we need to validate the sensor on the tire. Validation of the sensor, and at the end use it for road noise control. So feasibility in another word is linearity of the tire. Like this is your tire, it's a system, and we want to check the linearity of the tire with respect to an applied force. So here you apply a force in your tire, you apply a force F, and you measure the response of the tire, and we check if this response is linear. Then if the response is linear for an applied force, then we said then it is feasible to use a sensor on the tire. If the response of the tire is linear, that means we validated the feasibility. So how we did this step? We used a force sensor here. We used a force sensor. So this force sensor to measure the applied force on my tire, and at the output, the response of the tire, how we measured it? We measured it using an LDV or laser Doppler vibrometer. So it is a laser vibrometer to measure the displacement of the tire for an applied force. And we checked the linearity. How did we check the linearity? We computed the coherence we look to the coherence between the response of the tire, which is the velocity measured from the LDV, and the force sensor, or the force measured by the force sensor. So that is the first experiment we did to check the feasibility. Alright, so I have a tire, I apply a force, I look to the response, and if I have a coherence close to 1 in between the velocity and the force measured from the sensor and this velocity measured from the laser vibrometer, if I have a coherence more than or equal 0.85, 0.9, more than that, then it's considered to be a linear to a certain degree. Okay, and of course you have a limit of applied force. If you keep varying the applied force, then you can start seeing nonlinearity. Alright, so to mimic a car environment, we applied it on a quarter car suspension. So we didn't take a isolated tire, however we take a quarter car suspension, and on it we applied actually a force, and this applied force, it is according to the ISO standard good road profile. This is according to the ISO standard for a good road profile. Alright, so then the force applied is according to the ISO standard for a good road profile. It is applied on a quarter car suspension, and it's measured using a force sensor, and the response measured using a laser Doppler vibrometer. And here is the experiment we did. So you can see here I have a quarter car suspension. I apply here using a shaker, dynamic shaker, a force that mimics the good road profile according to the ISO standard, and using a laser vibrometer I scan the side wall, but also I scan the tread of the tire, and I look to the response. I get here I have a force sensor which measuring the force applied, so I get this force and I have the output from here, and I check the coherence between both. And here what did I obtain? So you can see you have in orange the coherence for the tread side, and in yellow the coherence for the side wall. And as you can see, we are very close to 1. So some questions: why we validated in the range of 250 Hertz, not more than that? And why we have this sheet or decrease in coherence at some specific frequencies? Well, I keep these questions to the Q&A session. So if you would like, we discuss them. Okay, why it is the frequency below? I just studied it in the range of 0 to 250 Hertz only, low frequency. Why I'm interested only in the at the low frequency range, and why we have this decrease in coherence at some specific frequency. We'll keep it to the Q&A session. And what is this? What these figures are? Well, simply those figures are a map for the side wall at a specific frequency, and the same for the tread side at a specific frequency. And what you can see here, at each point is the average for the overall area. Okay, so that's the average of the overall area for each frequency. It's plotted on this slide. All right. So you may wondering here to ask why I have like this kind of some places. Also, those interested, we discuss them during the Q&A session. So by this and having good coherence, we check the feasibility of using a sensor on the tire. So the next question that's coming in mind is where to put the sensor. Where is the best location for putting the sensor? The best location is where the highest strain is obtained. So how to find the strain? How to calculate the strain? I have experimentally found, or I experimentally measured the velocity or the displacement also using the LDV, laser vibrometer. Using the laser vibrometer, I have the velocity or the displacement, and then from this experimental data, from the displacement, I need to find the strain. Now, using an approximation model of the tire. And this work was done in one of our previous publications on which we studied the strain level on the tire tread and sidewall. For example, if it is on the sidewall, where is highest? Is it in the inner radius or at the outer radius of the sidewall? On the tread, for example, the same we did this, and we found that as a result that the tire tread area is where highest strain is obtained. So this area is where the highest strain is obtained. So then we decided to consider this location or these locations as a potential location of the sensor. So now if you go to this slide, we are putting our strain sensor from inside. So I get the tire out, and from inside I use 3 sensors. I put them here, I just mark them, and those are the 3 locations. I just use 3 sensors, okay? And they are located on the tread area. So now the next question is, what are the specifications of the sensor? So when talking about specifications, we need to keep in mind the mechanical durability of the sensor. It should be mechanically durable because it will be exposed to harsh environment such as repeatable deformation, irregular deformation, sudden deformation. So then it's harsh environment for the tire. So with a safety measure, with some safety margin, we found our specification. So subjected to discussion during Q&A session. Just here I need to mention the continuous transmission, which is very important for active structural acoustic control. So we need to have continuous measurements of the applied force to have a better performance in control or better control performance. Okay, so now those are my specification. Next is to choose the sensor and what type of sensor we will use based on the specification. In here and based on those specifications, we have chosen a sensor developed at Simon Fraser University by Prof. Woo Soo Kim and his team. Prof. Woo Soo Kim claimed on his paper developing a capacitive strain sensor for harsh environment use like in tire environment. And this transducer is embedded now. That's the transducer, capacitive strain transducer is embedded now from behind on the tread area. So now the next step is to check its response, compare its response with a force sensor, with our force sensor, and therefore checking the coherence between the force sensor and our capacitive strain sensor. Well, if the coherence is high, means our sensor is good enough to be used in road noise control. The question that may come in mind, if I have a force sensor, so why I need to look for different sensor, and so I can use that force sensor that I have. We'll keep the answer for this for the Q&A session. Here is the coherence between the CST and the reference force sensor. So for a good road noise profile, we saw that our sensor doesn't have really a good coherence. But if we have, let's say, a bad road profile, we may start having better coherence. Like if I am applying 25 Newton or 30 Newton, 33 Newton, so you can see the coherence becoming to be 1 or close to 1. But in case of good road noise profile, the sensor is not really very useful for road noise control. And therefore, in a good road, if you want to use that sensor in a good road profile, so therefore we need to improve the sensitivity of the sensor. If our road profile is not good enough, assuming 25 Newton road noise, so in that case I can use the sensor. So I'm assuming now I have a bad road profile. I'm applying 25 Newton, and I will check in the next slides the control performance when applying 25 Newton. So here we go for the active structural control. We choose first the best location for the actuators, and in here we used a least mean square pre-filter reference feed forward least mean square control structure, on which you can say those are your input and here are your output. So I have two actuators. I choose two actuators. Those are my actuators, those are my inputs, and those are this is my disturbance signal. Okay, this is your disturbance. It's a reference force sensor, or in the next experiment could be is the capacitive strain transducer. So this is a feed forward control using LMS. Feed forward control using LMS architect, on which those are your input. The sensor, I measure the vibration and I control the vibration using my actuator, and the disturbance here is the road noise. In one experiment should be the reference force sensor, and I measure the noise reduction. In the second will be my capacitive strain sensor, and I measure the noise reduction. Here is a Opal RT speed goat real-time data acquisition system, on which I have these two output and the other inputs. Okay, coming to the system, and here is MATLAB Simulink process, and that's what we obtained. You can see that the capacitive strain sensor has better noise reduction compared to the reference force sensor. As future work, I recommend improving the sensitivity of the strain sensor to really reach high coherence at good road noise profile. Also I recommend to test this type of sensor, which is developed by Professor Walid Musa and his team at University of Alberta, on which they are using stood like sensor. so it could be integrated as a stud on the tire and can be used to measure the road noise. At the end, I would like to thank Auto21 networks of centers of excellence of Canada for supporting this work. And because we are talking about automotive applications, I will present to you at the end this video, which is an electric vehicle car proudly made in Lebanon. It will be my pleasure to discuss with you further about my research topic in the Q&A session. See you there.